The last time we discussed cross-site request forgery. Today I want to mention a less known attack which is called cross-site script inclusion, which essentially also abuses of cross-site request. Contrary to cross-site request forgery, cross-site script inclusion is an attack against confidentiality. The attack is simple. The key idea is that some benign site might assemble scripts depending on session data, and this session data might contain confidential information. In this attack, the victim first authenticates at a trusted service, say good.com, and later visits the attacker website, say evil.com. Now the attacker loads a script from good.com using a script tag, and since the script inclusion request contains the victim cookies, the script is generated so that it contains some private information on the victim, say a credit card number. Now, since the script is included in the attacker origin, the attacker can try to use JavaScript to exfiltrate the secret from the script and leak session data. To understand how the attack works, I have to mention a little bit about scoping in JavaScript. JavaScript is pretty strange in terms of scoping because variables live all in the global scope by default, even when they are declared inside a function. It is possible to make variables local to a function by using a var keyword. Let's check an example here. Here we're declaring a global variable with value 5, and then we define a new function, global function, which contains internally two more variables. One is a local variable because it's anticipated by the var modifier, while the other variable is global variable 2, which is indeed global because we don't mention the var modifier here. So although this variable is declared within a function, it's still visible outside of the function. And you can also declare global variable in JavaScript by defining properties over the window object, like in this way. Contrary to what happens in C++ or Java, which make use of block scoping, JavaScript utilizes the so-called function scoping. This means that the JS engine creates a new scope for each encountered function. So an identifier which is locally within a function is associated to the function scope, and blocks are essentially ignored. So if you declare a variable inside a block, that variable is still visible inside the whole function, unless you enforce block scoping by using the let keyword. In general, let is a much better option than var, because as a programmer we're much more used to block scoping than to function scoping. So most of the var should actually be replaced by lets. Let's take an example in this slide. So here we have a variable age which is set to 100, and this means that this conditional check will succeed, and inside this conditional check what we do is computing a new variable, dog years, which is computed as age times 7, and then we log the content of the dog year variable. Then, when we do after the branch is logging again the value of dog year variable. What you would expect in standard programming languages is that this line will trigger an error because dog year does not belong to the scope. But this is not the case in JavaScript, because although this dog years variable is declared as a local to the function, it's still in the function scope. So if you don't want to see dogs year in this line of code, you have to use let here. Now that we understood a little bit of the quirks of scoping in JavaScript, let's have a look into how Xssi work. So the idea is the following. So let's assume I have a snippet of a file at pay.js, which is a payment script at good.com. The goal of the attacker is to be able to exfiltrate some very secret credit card number from the script. In this case, the attack is trivial because what the attacker can do is just loading the script using a script tag, and since info is declared as a global variable because there is no var keyword in front of it, the attacker gets visibility of the info variable and can just call the leak function over it and exfiltrate the secret. So this is actually super simple. Of course, programmers might be smarter than this and realize that they should make function local to variable. So in this case, we revise the doPayment function so that the info record, which contains the credit card number and the amount to be paid, is declared as local to the function doPayment. What's the problem of this function? The problem is that at the end we call the JSON.stringify function on top of the info variable, and we explicitly ask, using the second parameter of the JSON.stringify function, that we would just want to print the content of the amount field of the JSON. Because indeed, very secret is secret, and we don't want to expose it out of the doPayment function. However, what the attacker can do is exploiting the fact that JavaScript is a very dynamic language, so essentially also JSON.stringify is a global element which can be modified by the attacker. So in particular, what the attacker can do is first redefining JSON.stringify as a function which takes two parameters and just leaks the first parameter, and then embed the script from the inline side, so that now, rather than calling the standard JSON.stringify, the attacker control JSON.stringify is called and the secret is leaked. Other attacks are enabled by the strange way in which inheritance is implemented in JavaScript. Because JavaScript has objects, but inheritance is not based on classes, but directly on the objects themselves, and in particular on the notion of prototype. So in this example, you can see that I'm declaring a variable O1, which is an object with one field A set to 1, and by default, since this is not inheriting from any other object, this object has a prototype which is called object.prototype, which is like the father of all the possible objects in the object hierarchy. Then at the second line, I'm creating a second object O2, and I use the object.create to inherit stuff from O1. So now the prototype of O2 is O1, which means in particular that when I call console.log on A2.a, the correct answer is still printed. So I print 1 because A is provided by the prototype O1. So the key idea is that method invocation and field accesses traverse the prototype chain looking for a valid implementation up to the root, in the worst case, which is the object.prototype object, which is the root of the object hierarchy. So a good way to try to exfiltrate the data is shown in this example. So here again we have the function doPayment. We have a data array which contains some credit card numbers, and at some point in the implementation we call data.slice, which essentially picks just a single element from the array. Again, the problem is that data.slice is not really defined in the global scope, but is defined through the array prototype. And since array prototype is visible indeed in the global scope, what attacker can do is redefining the slice function so that when we call the slice over an array, we don't call the correct implementation of the slice, but we just call the attacker control variant of the function. So in this case, what we can do is that we redefine the slice method of the array prototype in a way that rather than slicing the content of the array, what we do is just leaking the object which contains the array. So this is another variant of the attack where attacker is able to exfiltrate data. How can we prevent Xssi? This is quite simple, because the idea is that although this attack is different from CSRF, the attack vector is the same. So any of the defenses we propose against cross-site request forgery is useful against Xssi. However, please notice that Xssi makes the attack surface on web application even larger, because we also have to care about dynamically generated script. Of course, a good solution for this is also relying on defensive programming practices. So for instance, I might want to redefine my own serialization function so that the attacker cannot redefine it in a way that I call attacker control code. However, there is a much nicer and general solution to prevent Xssi, which leverages the same origin policy. And the idea is that we never generate script code based on the session cookies, but we always pull the script code directly from a static file. So what the attacker can do is loading a static file, and all the sensitive and dynamic data values are kept in a separate file which cannot be interpreted by the browser as JavaScript. So for instance, we store this data as a JSON file on the server, and when the JavaScript file is executed, it retrieves the data by using Xssi. In this way, when the attacker tries to load the script from the attacker control origin, the request for inclusion will be a cross-origin request. And for the attacker, it will not be possible, due to the same origin policy, to check into the content of the response and get access to the secret data. Of course, if you want to allow access to the secret data to authorized third parties, you can use CORS to selectively grant access to these entities. Here you can find a few papers which I strongly recommend. This is a classic paper on cross-site request forgery and robust defense techniques for this. Here you can find another paper where we discuss how we can use machine learning to identify room for cross-site request forgery in real-world applications. And if you're curious about Xssi, this is a great paper on the topic. So this basically concludes the main content. What I would like to show you and assign you is some exercises. So if you go to this URL, porswigger.net/web-security/CSRF, you can find a lab on cross-site request forgery. You can register to this web application, it's for free. It contains a very nice set of labs, including this cross-site request forgery lab. You can review a little bit on how cross-site request forgery works, and you will find different challenges here, which you can try to solve using your own browser. I think it's relatively simple, but quite instructive, so please take a look into this, and if you have troubles, you can write me, and we will discuss together how to solve this.